Cloud security is absolutely exploding in demand right now. The average data breach costs companies just under $5 million. And considering how AWS powers most of the applications that we all use every single day, the need for engineers who understand cloud security has never been higher. Whether you're an IT professional or an engineer looking to specialize in cloud security, or you're just trying to land your first cloud role and need to understand the fundamentals, then this is the skill that will set you apart from your competition. Hi, I'm Suleiman. I spent the last decade working in tech, and I've helped more than 700 students break into cloud engineering. And here's what I've noticed. Most engineers and even organizations surprisingly approach cloud security completely backwards. They build their applications first, get everything working, and then they try and bolt on security at the end like it's an afterthought. And unfortunately, that's where things unravel because security needs to be woven into the fabric of your architecture from the very beginning. By the end of this video, you will understand how AWS cloud security actually works. From IAM, which controls who can access what, to encryption that protects your data both at rest and in transit, to network security that keeps attackers out. And don't worry if you've never built anything in AWS or if some of these concepts sound unfamiliar, I'm going to break down everything step by step so you understand exactly how it all works. Let's start with the most fundamental concept, the shared responsibility model. Here is a question that trips up almost everyone new to AWS. If something gets hacked, whose fault is it? The answer is both. And understanding exactly where that line sits is critical. But first, let me explain what's actually happening when you use AWS. You're not buying physical servers. You're renting access to AWS's massive infrastructure. Their servers, their storage, and their networking equipment sitting in data centers around the world. This is what we call the cloud, and that's what it actually means. Your applications run on hardware that AWS owns, but you control what happens on that hardware remotely. So who's responsible for what? AWS calls this the shared responsibility model. And once you understand it, the logic is very simple. There are two layers of security here. The physical infrastructure layer, so your buildings, your servers, your cables, your power systems, and the actual software layer, so your applications, your data, your settings, and access controls. AWS handles the security of the cloud. This is the physical infrastructure and the foundational services. Physical security of data centers are your guards, your cameras, your biometric access, your multiple checkpoints. No one walks into an AWS facility and touches the servers. There's also hardware maintenance, so ensuring servers are functioning, replacing failed components, securing network equipment. The virtualization layer, so the technology letting multiple customers share the physical servers without accessing each other's data. Think of it like an apartment building. Same physical structure, but you can't enter your neighbor's flat, right? Then we've got the underlying network infrastructure, so securing data flow between data centers and protecting their core network from attacks. All of this is AWS's job, so you don't have to worry about it. You handle the security in the cloud. This is everything on top of that infrastructure. So your account access, who gets credentials, what permissions they have, and what they can launch or delete. Your application configuration, so keeping software patched, using secure coding practices, fixing vulnerabilities. Data encryption, so AWS provides the tools, but you turn them on and configure them. Network architecture, so which resources face the internet, which stay private, and how they communicate. Operating systems, so if you launch a Linux server, then you can patch it just like you would in your own office. Now, this model is good news. You don't maintain the hardware or manage the networking equipment, right? AWS will handle that for you. You just focus purely on securing your applications and your data. But you can't assume everything is automatically secure because AWS gives you the tools and you have to use them. So now that you understand that AWS is responsible for securing the infrastructure and you're responsible for securing what you build on it, the next question becomes, how do you actually control who can access what in your AWS account, right? Because here's the thing. When you're using AWS, you are constantly performing actions. You are clicking buttons in the AWS console to launch a new server. You're running commands to upload files to storage. You're writing code that needs to read from a database. Every single one of these actions is something that needs permissions to happen. And this is where identity and access management comes in. IAM is a system that controls who can perform which actions on your AWS resources. And when I say who, I don't just mean people, I also mean applications, scripts, and AWS services, and soon AI agents, right? That need to interact with other AWS services. Without IAM, you'd have a massive security problem. Either everyone and everything would have full access to your entire AWS account, meaning that anyone could launch servers, delete databases, or access sensitive data, or no one could do anything at all because there'd be no way to grant specific permissions. IAM solves this by letting you define precisely who can do what. And here is why this matters so much. Almost every security breach in the cloud can be traced back to misconfigured IAM permissions. Someone or something had access to resources or actions that they shouldn't have access to. IAM operates on something called the principle of least privilege. This means if someone needs to upload files to a storage bucket, you give them permissions to upload files to that specific bucket. Not permission to delete files, not permission to access other buckets. Just exactly what they need and nothing more. Now, why be this strict? Because every extra permission that you grant is a potential way for an attacker to cause damage. If someone's credentials get stolen and they only have permission to upload, the attacker can only upload files. But if those same credentials have permission to delete the entire database, then the attacker, well, you guessed it, can delete your entire database. The more permissions something has, the more damage it can do if it gets compromised. Now, when you first create an AWS account, you get login credentials, an email and a password. These credentials give you access to what's called the root user. And the root user is special because it has completely unrestricted access to everything in your AWS account. It can launch servers, it can delete them, it can access every single database, it can change your billing settings, even close your entire AWS account. There are literally zero restrictions. Think about what that means from a security perspective. Every time that you log into AWS with those credentials, from your laptop, from a coffee shop, from anywhere really, you're using credentials that have unlimited power over your cloud infrastructure. So if someone steals those credentials, i.e. maybe your laptop gets stolen, maybe you accidentally install malware, maybe you log in from a compromised network, they now have complete control of your AWS account. They could delete everything that you've built. They could download all of your data. They could rack up hundreds of thousands of dollars in charges. This is why the first and most critical security practice in AWS is simple. Stop using the root user for everyday tasks. You should only use it for the rare occasions when you absolutely have to, like changing your billing information or closing your account. For everything else, like launching servers, deploying applications, managing databases, you use IAM. IAM gives you 3 different tools to manage permissions, users, roles, and policies. And let me explain what each one does and when you'd use it. An IAM user is how you give a specific person access to your AWS account. So when you create an IAM user, you're essentially creating a separate login for that person with its own set of permissions. So you give them a password so they can go and log into your AWS console. That's the web interface where you just click around and configure and manage things, right? Or you can generate what are called access keys for them. Access keys are credentials that let you interact with AWS programmatically, meaning through code or command line, instead of just clicking buttons in the web browser. Now they consist of 2 parts, an access key ID and a secret access key. Together, they authenticate you when you're making automated requests to AWS. And here is what most people don't realize about access keys. They never expire. They work forever until you manually delete them or rotate them. This means if someone steals those access keys, maybe they find them in your code, maybe they're in a file on a compromised laptop, they can keep using them indefinitely until you notice and revoke them. This is why you need to be extremely careful with access keys. Never commit them to GitHub or any sort of code repository. Never hard code them directly into your application. And obviously, but you'd be surprised, never send them in emails or Slack messages. But here is the thing. IAM users are really designed for humans who need ongoing access to your AWS accounts. And what about your applications? Well, this way you use IAM roles, giving applications temporary permissions. Well, here's a scenario that happens all the time. You write some code, maybe it's a Lambda function, which is just code that AWS runs for you, so also known as serverless. And that code then needs to read files from S3, which is AWS's storage service. So you're going to have to give Lambda permission to access S3. Now, your first instinct might be to create an IAM user for it and generate access keys, but that actually leads to a problem. Where do you store those access keys so your Lambda function can use them? Now, you can't just put them in your code because they're going to be visible to anyone who can see your code. You need some secure place to store them, and then you need to rotate them often for security. And if you have hundreds of functions or applications, you're now managing hundreds of sets of permanent credentials. Now, can you see how that's just not practical whatsoever? Right? That's where IAM roles come in and solve this problem. Instead of creating permanent credentials with access keys, an IAM role is a set of permissions that something can just temporarily assume. Now let me explain. When you create that Lambda function, you assign it to an IAM role that has permissions to read from S3. When the Lambda function runs, AWS automatically and temporarily gives credentials based on the role. Those credentials work for about an hour and then they expire, and then AWS automatically generates new ones. Your code never needs to know about the credentials or store them anywhere. It just says, I need to read from S3, and AWS will handle the authentication behind the scenes using that role. And because these credentials are temporary, even if someone intercepted them, they'd only work for a short window of time before expiring. But whether you're using IAM users for people or IAM roles for applications, you still need to actually define what permissions that they have. And that's exactly where policies come in. Policies define what someone can actually do, and every policy has a few key parts. There's the effect, which is either allow or deny, so it's pretty straightforward. There's the action, which specifies what someone is trying to do. In AWS, everything that you do is an API call. When you click a button to launch a server, behind the scenes, you're making an API call called EC2 run instances. The action in a policy specifies which of these API calls are allowed. Then there's the resource, which specifies exactly which AWS resources this applies to. With our example here, it would be EC2. And optionally, there's a condition, which lets you add extra requirements. For example, only allow this action during business hours or allow it if the person used MFA to log in. And here is why this level of granular detail matters. Let's say that you build a web application where users can upload profile pictures. Those pictures get stored in S3, so your application needs permissions to upload those images. You could just give your application full S3 permissions, meaning that it can delete the buckets, it can create the buckets, it can upload files from anywhere, it can delete the files from anywhere, it can change permissions on any bucket. But what happens if your application has a security vulnerability and gets compromised? Well, an attacker now has full S3 permissions. They could delete all of your S3 buckets and everything inside them. They could download sensitive data from other buckets. They could modify files that your application depends on. But with a properly configured IAM policy, you can be so much more specific. You can create a policy that says that you can perform the S3 put object action, which is uploading a file, or that you can only upload a file in the bucket called user profile pictures. Now, if your application gets compromised, all an attacker can do is upload files, right, to a specific bucket. That is it. They can't delete anything. They can't read anything, and they can't access any other buckets. And this is what the principle of least privilege looks like in practice. And it's really important for you to get an understanding of this. With least privilege, you grant only the exact permissions needed. And in this case, you've seen how that limits what the attackers can do. So here is what you need to remember. IAM controls who can access your AWS resources and what they can do with them. Get IAM wrong, and attackers can bypass everything. Get IAM right, and you've built a solid foundation for security. But controlling access alone isn't enough. You also need to protect the data itself, even if someone manages to access it. And that's where encryption comes in. So let's say you have an S3 bucket and you've configured IAM perfectly so only authorized people and applications can access it. But that data is sitting on a physical hard drives in an AWS data center, right? Now, what happens if someone bypasses all of your access controls? Maybe someone with physical access to the data center acts maliciously. If your data is just sitting there in readable form, anyone who gets their hands on it can read it. And this is where encryption comes in. Encryption transforms your data from readable text into scrambled words using mathematics. Now, the only way to unscramble it back into readable form is with a special piece of information called an encryption key. Only someone with the encryption key can unscramble it back into readable text. In AWS, you need to encrypt data at two different points, at rest and in transit. Encryption at rest means encrypting data while it's sitting on a storage device. So when you store your files in S3, that data is physically written to a storage media somewhere in an AWS data center. So don't forget, that's the big picture when we're using the cloud. Without data encryption, if someone gains physical access to those hard drives, then they could plug that drive into a computer and read all of the data directly. Your IAM policy don't matter anymore because they're bypassing AWS entirely and accessing the raw hardware. With encryption at rest enabled, that data is scrambled before it's even written to the disk. Even if someone physically steals that hard drive, all they see is encrypted words that they can't read. AWS makes this easy to enable. For S3, you can just turn on default encryption so every file uploaded gets automatically encrypted before being stored. And you can do this essentially for everything that you use in AWS. And it's all done automatically and your applications don't need to change at all. Now that's when data is at rest, and that's where encryption in transit comes in because it protects data while it's traveling across the networks. Well, here is what's actually happening when data moves across the internet. Your data gets broken into small packets. Think of these as tiny chunks of information. These packets travel from your source to your destination, potentially passing through dozens of different routers and network devices across the world. Anyone who controls any of those devices along the path could potentially intercept and read those packets. Maybe you're sending customer data from your application to your database. Maybe a user is sending their password to your login page. All of this data is traveling across networks. Without encryption in transit, it's traveling in the same readable form again, which means anyone along the path could intercept it and read it. Now with encryption in transit, the data is scrambled before it leaves the source and only unscrambled when it reaches the destination. Anyone who intercepts it in between just sees the encrypted words. For example, when you see HTTPS in a web address instead of HTTP, that S means that the connection is encrypted. Everything sent between your browser and the website is encrypted. In AWS, this happens automatically for most things. When your application talks to AWS services, such as uploading files to S3, querying a database, making any API call, AWS encrypts that traffic by default. And when it comes to traffic between your users and your applications, you need to configure encryption by setting up HTTPS on your servers or your load balancers. Now, earlier I mentioned that the only way to unscramble our data is with encryption keys, which then naturally begs the question, if I've got these keys, where would I actually store them? Now, you can't save them on the same server as your encrypted data, right? That defeats the entire purpose. That's like locking your front door and leaving the key under the doormat. Instead, AWS Key Management Service, or KMS, solves this problem. When you enable encryption for an AWS service, KMS generates an encryption key and stores it securely. Your encrypted data gets stored in S3 or your database, wherever it belongs, right? But the encryption key itself actually stays locked inside of KMS. Here is how this works. Firstly, the encryption keys never leave KMS. When you need to decrypt data, which just means to unscramble the words into readable form, you don't get the key. Instead, you send the encrypted data to KMS. KMS decrypts it using the key stored inside it, and then KMS sends it back to the decrypted data. Notice how the encryption key itself never travels anywhere. Secondly, access to KMS is controlled by IAM. Even if an attacker downloads all of your encrypted data from S3, they still can't decrypt it without IAM permissions to use the KMS key. They would need to compromise both your data storage and your IAM credentials with specific KMS permissions. Can you now see how having multiple layers of defense just protects you? Thirdly, KMS logs every time a key is used, who used it, when, and for what. This creates an audit trail of all encryption and decryption operations. KMS also offers different types of keys. AWS managed keys, which are created and managed entirely by AWS, so you can't see or control them. AWS will handle everything. And also customer managed keys, which gives you full control. So you create the key, you define it, who can use it, you have to rotate it, or you delete it. Most organizations use customer managed keys for sensitive data because they provide more control. The key policy which is attached to each KMS key defines exactly who can use it and for what purposes. And by the way, this is separate from IAM policies, providing you with another layer of control. So far, we've covered IAM, which controls who can access what. We've covered encryption, which protects your data both at rest and in transit. But there's another critical layer, controlling how traffic flows through your AWS environment. Because here is the thing, even if you have perfect IAM policies and everything is encrypted, you still need to control which systems can talk to which other systems. Can someone on the internet connect directly to your database? Can your web servers access your internal systems? Can traffic from one application reach another application's resources? This is what network security is about, controlling the flow of traffic at multiple levels. And the reason that you need multiple levels is something called defense in depth, which we've touched on lightly throughout. So even if an attacker bypasses one security control, they hit another barrier, then another, and then another. So let's start with the foundation, your VPC. When you create a VPC, you're creating your own isolated network within AWS. What this means is that your VPC is completely separated from other AWS customers' networks, and it's separated from the public internet. Nothing can enter or leave your VPC unless you explicitly open a path for it. Within your VPC, you divide things up using subnets. A subnet is just a section of your network. Now, you might have one subnet for your web server, another for your servers, another for your application servers, another for your databases. And there are two types, both public subnets, which can connect to the internet, and resources in a public subnets can have public IP addresses that are reachable from the internet. Then you've got private subnets, which cannot connect to the internet. Resources in private subnets only have private IP addresses that are invisible to the outside world. This architecture solves a critical security problem. Your databases and internal systems shouldn't be accessible from the internet. They should obviously be completely hidden, right? So you have to put them in private subnets where they're invisible to the outside world. But here is where most people get confused. Sometimes resources in your private subnets do need to reach out to the internet. Your database server needs to download updates. Your application server needs to call an external API. So how do they access the internet without being exposed to incoming traffic? Well, that's where NAT Gateway comes in. NAT stands for Network Address Translation. A NAT gateway sits in a public subnet, meaning that it has internet access. So when a resource in a private subnet needs to reach the internet, it sends traffic to the NAT gateway. The NAT gateway forwards that traffic out to the internet. From the internet's perspective, the traffic is coming from the NAT gateway's public IP address. So when the response comes back, the NAT gateway forwards them to the private resource that just made the request. And here is how this helps you from a security perspective. NAT gateways only allow outbound traffic. So your database can initiate a connection to download updates and the response comes back. But someone on the internet can never initiate a connection to your database through a NAT gateway. It just blocks all the inbound connection attempts. And this is just at a VPC level. You also need to go deeper and control traffic at the next level, which is the subnet level. Network ACLs or NACLs control traffic at the subnet level. Every subnet has a NACL attached to it. When traffic tries to enter or leave the subnet, NACLs evaluate it against a set of rules. NACLs are stateless, which means that they don't remember connections. They evaluate each packet independently. Remember, we mentioned packets earlier as small bits of data, right? So if a packet tries to enter your subnet, the NACL checks the inbound rules set at the subnet level. If the rules allow it, then the packet enters it. When the response packet tries to leave the subnet, the NACL checks the outbound rules separately. So it doesn't remember that the inbound packet was allowed, so you have to explicitly set the rules for both directions, both inbound and outbound. Now, here's something important about how NACL rules work, right? When you create NACL rules, you assign each one a number, like a rule 100, a rule 200, rule 300. AWS checks these rules starting from the lowest number and working its way up. The moment that it finds a rule that matches your traffic, it applies that action and stops checking. So if you have a rule 100 that denies traffic from a specific IP address and rule 200 allows all traffic, the IP address gets blocked because AWS checked rule 100 first, found a match, and never even looked at rule 200. Network ACLs support both allow and deny rules. This makes them super useful for explicitly blocking known bad traffic. So if you detect malicious activity from a specific IP address, you can then add a deny rule at the NACL level to block all traffic from that specific address. But network ACLs are fairly broad. They apply to the entire subnet. So every resource in the subnet gets the same rules. For even more precise control, you use security groups. Security groups work at the individual resource level. So every EC2 instance, every database, every AWS resource has a security group attached. And security groups are stateful, which is different from network ACLs. Stateful means that they remember connections. So if you allow inbound traffic on port 443, the security group automatically allows the return traffic. You don't need separate outbound rules for responses. Do you notice how that's different to NACLs that we just discussed? This inherently makes security groups much easier to configure. You only define the traffic that you want to allow in, and then responses are automatically handled. Security groups only support allow rules, not deny rules. By default, all inbound traffic is blocked unless you explicitly allow it. By default, all outbound traffic is allowed, but you can restrict it if needed, right? Now here is something handy. Security groups can only reference other security groups. Let's say you have web servers and you have database servers. You create a security group for the web server and a security group for the database. The database security group can have a rule that says allow traffic from the web server security group. Now, as you add more web servers, they automatically can get database access as long as they have the web server security groups attached. And here is why this matters. Without this feature, you'd have to use IP addresses in your rules. Now let me explain. Every time that you launch a new web server with a new IP address, you have to manually update your database rules to allow that specific IP. With security group references, you're saying allow anything with the web server security group. So new web servers automatically get access without you having to touch the database rules. Now, I want to show you how all of these pieces come together in practice. Let's say you're building a web application with 3 tiers, a web server, application server, and a database. Here is how you set it up the security layers. Layer 1 is your web servers. So your web servers sit in a public subnet because users need to reach them from the internet. They have public IP addresses. The subnet's NACL allows HTTPS traffic from anywhere on the internet. Each web server has also a security group that allows inbound traffic on port 80 or 443, HTTP and HTTPS. Then we've got layer 2. Your application servers. So your application servers sit in private subnets with no public IP addresses and no direct internet access. The subnet NACLs only allows traffic coming in from the web server subnet. Each application server has a security group that only allows traffic from the web server security group, right? So not from specific IP addresses, but from anything within that specific security group attached. Layer 3, Databases. So your databases sit in a private subnet, even more restricted. The subnet's NACL only allows traffic from the application server subnet. Each database has a security group that only allows traffic from the application server security group on the database port, like 3306. Now, let's trace what happens when a user makes a request step by step. Step 1. A user on the internet tries to access my website, right? cloudengineeringacademy.io. Their request will first hit the web server's subnet. Step 2. The NACL at the subnet level checks, is HTTPS traffic allowed? Yes. The request passes through. Step 3. Now the request reaches the specific web server. The security group checks, is traffic on port 443 allowed? Yes, then the request gets through. Step 4. Your web server receives the request. Let's say that the user wants to see their account information. The web server needs to get that data. So it contacts your application server. Step 5. The application server's security group checks. Where is the request coming from? Does it have the web server security group? Yes, the request is allowed. Step 6. The application server now needs to get the actual account data from your database. It sends a query to the database. Step 7. The database security group checks. Does this request come from the application server security group? Yes. Query allowed. Step 8. The database sends back the account information. Because security groups remember connections, the data flows back automatically through the application server, back to the web server, and finally to the user. Do you notice a pattern? At each layer, there's a security check happening. Now let's see what happens if an attacker tries to directly access your database from the internet. Scenario 1. An attacker tries to connect to the database directly from the internet. First offense here is that the database is in a private subnet with no internet gateway route. There's literally no network path from the internet to reach it, so the attack gets blocked. Scenario 2. An attacker somehow gets into your VPC and tries to access your database. So the second defense here is that the database security group only allows traffic from application server security group, right? So the attacker's traffic doesn't have that security group attached, so the attack gets blocked. Scenario 3. An attacker compromises an application server and tries to access their database. The third defense here would be that they can only access the database on the specific port allowed by the security group, like port 3306. And even then, all of the actions are limited by the IAM role attached to the application server, so they can only do what the role permits. This is defense in depth. Multiple independent layers that each need to be bypassed. And this is how you build secure systems in AWS. IAM controlling who can access what, encryption protecting data even if accessed, and network security controlling how traffic flows between your resources. So, cloud security is not something that you can just configure once and forget about it, right? Security is a continuous ongoing process that's always subject to change as you build your applications out. The security controls that we've covered: IAM with release privilege, encryption at rest and in transit, proper key management, and layered network security. These are the real foundations that make up cloud security in AWS.